This is section 2.3, Polynomial Functions. It is also connected to the AP Precalculus Standards 1.4, which is Polynomial Functions and Rate of Change, and the AP Standard 1.6, which is Polynomial Functions and End Behavior. So the first part is to talk about some definitions. So a polynomial is a function that contains positive integer exponents. The degree of a polynomial is the highest exponent, and the leading coefficient is the coefficient on the term with the highest exponent. And then when we talk about writing a polynomial in standard form, it means we put it in order from the highest to lowest degree or highest to lowest exponents. So we're going to start by talking about end behavior. So there are 4 different categories of polynomial end behavior we can look at. So we're going to use the degree, whether or not it's even or odd, and the leading coefficient, whether or not that's positive or negative. So the first one we're going to look at is odd and positive. So odd and positive is going to be headed down to the left and up to the right. And you can fill in like dashed lines. It might look like that, like a cubic. It might have more minimums and maximums in there. It might be a line. A line would be odd and positive. So what we're going to do is we're going to talk about the end behavior, and we're going to write it in limit notation. So the way that we write limit notation is, first of all, we're going to start to the left. So we're going to say the limit as x approaches negative infinity of f of x. And so that's that whole thing, what we just wrote, just means as we go to the left. So if we look at this graph, as we go to the left, our graph is going down. So we would say negative infinity. Then the second part is we're going to say the limit as x approaches positive infinity of f of x. So again, that whole thing that we just wrote means as we go to the right, our graph goes up, positive infinity. So next we're going to look at odd and negative, which is just going to be the opposite of this. Again, if you want to put some dashed lines in there, you can. So our end behavior, our limit as x goes to negative infinity. This time, as we go to the left, it goes up, so it'd be positive infinity. And the limit as x goes to positive infinity, our graph goes down, so it'd be negative infinity. Okay, our last 2 types are even and positive, and even and negative. So even and positive, we can think of like a positive quadratic value that has an a value that's positive and it opens up. So you could think of a quadratic. So for that, our end behavior, the limit as x approaches negative infinity, is going to go up. So it's going to go to positive. And as we go to the right, it's also positive. So notice again, that first part of the limit notation that I'm writing never changes. So even and negative would be maybe something like that. So the limit as x goes to negative infinity of f of x would be negative infinity, and the limit as x goes to positive infinity of f of x is also negative infinity. So you can see the only things that are changing are these parts right here. So everything else is staying the same because it means as we go to the left and as we go to the right. The part that's going to change depending on the type of polynomial we're looking at is the end behavior. So is the polynomial going up or is it going down? So for example, we have g of x equals 2x cubed minus 3x squared plus 1. So the degree of this function is 3, so it is odd. And the leading coefficient in this case is 2, so the leading coefficient is positive. So the end behavior for this function, we would say the limit as x approaches negative infinity, we're looking right here on this one, of g of x. Notice my function changed, so I'm making sure that I'm labeling it g of x and not f of x. So g of x would be negative infinity, and the limit as x approaches positive infinity of g of x is positive infinity. So that's how we handle end behavior. Okay, so this one we are looking at an example and we're talking about average rate of change. And then we're going to also talk about what local minima and maxima. So the first one says the average rate of change between -3 and -2. So I just want to remind you these are both x's. So I'm going to use this in red. I'm going to show those 2 points. So -3 is right there on my graph and -2 is right there on my graph. So you can set up change in y over change in x. If it's a graph, I would just count. So the thing you want to keep in mind is the y-axis is going by tens. So we're going from positive 70 down to -20. So we went from 70 to -20, which is a decrease in 90. So we went down 90 and then we went over 1. So our average rate of change for that one would just be -90. Okay, I'm going to use a different color here. So let's look at the next one. So again, these are my x values. So 0 is right here, and then 2 is right there. So if I count my slope, my rise over my run, I'm going up 20 over 2. So positive 20 over 2 gives me a average rate of change of 10. Okay, local minima. So we can talk about global means overall the highest point on the graph. Because we have this graph is going up and down forever, we don't have a global maximum or minimum, but we do have local maximums and minimums. So we have a local minimum right here at -2, -20. And then we have a local maximum right here at positive 220. So those are local minima, local maximum is just relative to the points around it. It's a low point or a high point. Okay, so our last example here is multiplicity. So multiplicity means that if you have a repeated 0, your graph is potentially, if it's an even number of zeros, then that means your graph is going to bounce off of the x-axis or turn around and head back, not pass through. So odd multiplicity means it passes through the x-axis. Even multiplicity means it bounces off of the x-axis. So if we look at this example, so these are two separate examples. So the example on the left, we have two zeros. We have x equals -2 and we have x equals +1. So if you can see, this number right here tells me that -2 is a 0 3 times. So this has a multiplicity of 3, which means it would pass through -2. Whereas the 1 has a multiplicity of 2. So that's an even multiplicity, so that means it would bounce off of 1. So if I were to graph this, let me just sketch a rough graph here. This is, so if we count up our degree, this is a degree 5 polynomial, so it's going to be, and it's odd and positive, so we know it's going to start down on the left and head up on the right. And so we know that it passes through -2, so if we, but it's not going to be, it's going to kind of flatten out a little bit like that if you were to graph it, and then it's going to bounce off of 1. So that's what that graph would look like. So we can tell just by looking at a graph if there's an even multiplicity. So for example, we can look right here. We know that there is an even multiplicity at x equals 0. And we know that because it turns around and bounces off of it. So both of these are examples, and they help us when we're looking at a graph. We can determine, hey, maybe there's more than one 0 at that location.